All right, so we're going to continue these. Let me scoot up just a little bit on this. So remember problem 5, I just want to make sure that I finished it in the last video. So if you look at this as a fraction, it turns out that the energy that's coming out of a sunspot at 4,500 Kelvin compared to the surface of the sun, the energy coming out of from the sunspot is only 36% of the energy coming out of the actual surface of the sun. All right, so and it's just because of the temperature and the fact. So you just divide. I know I did this in the other video, but you just divide 4,500 to the fourth power divided by 5,800 to the fourth power, and that's how you get 0.36, which of course is 36%. All right, let's do the next one, number 6. It says here the solar wind carries away the mass from the sun at a rate of 2 million tons per second. All right, so this is just the solar wind. And they give us the fact that a ton is 1,000 kilograms. All right, at this rate, so we got to use that rate. How long would it take the sun? How long would it take for all the sun's mass to escape? All right, so we're just doing number 6 here. All right, so let's switch to this. Okay, so hold on. Let me go back to this. Just a second. Not sure if you're seeing this. Come on. Okay. Where's the? Sorry if you're. Did I mess this one up already? Let's see. Alright, so you got this. Where is the screen thing? Okay. Alright, I'll have to see if I did that right. Alright, so let me switch this. Okay, so hopefully you're seeing this. So here it is. I set this up right here. And come on. So the rate is 2 million tons per second. Right, 2 million tons, which that 1 ton is 1,000 kilograms. So a million, of course, is times 10 to the 6th, right? So 2 times 10 to the 6th, and then a ton is 1,000 kilograms, so it would be times 10 to the 3rd. Remember, you can just do this in your calculator, but if you don't really have to, because of course, if you have the same base and you're multiplying, right? 10 to the 6th times 10 to the 3rd, you just add the exponents, right? So it becomes 2 times 10 to the 9th kilograms per second. So that's the rate. And so the rate is equal to the mass of the sun divided by the time, right? And of course, that's in seconds. And so that's the rate. Once you have that, right, you take this equation right here and rearrange it algebraically, and you solve for t, which is really simple. You just multiply both sides by t, divide both sides by r. Basically, the t and the r change places. All right, so we know this is the r, 2 times 10 to the 9th kilograms per second. So that goes in the denominator. And of course, we have to look up the mass of the sun. And so the time. So here's the numerical part. The time is equal to the mass of the sun, which is 2 times 10 to the 30th kilograms. That's a 3. It's supposed to be a 3 kilograms divided by 2 times 10 to the 9th kilograms per second. All right, and of course the kilograms will cancel, and then you get 1 over seconds. The seconds comes up to the numerator, so here, oh, we're not seeing that, sorry. All right, so, whoops, here, let's restart that. Let's see, there we go. All right, so we were just calculating this. So this, the time turns out to be 1 times 10 to the 21st seconds. And then, of course, we got to change that to years just to make more sense of it. Here's how we change this to years, of course. I know that there are, of course, 60 seconds, right, in 1 minute. Always try to use MIN for minute because that distinguishes it from meter. All right, and of course, there's 60 minutes in 1 hour. And then, of course, there's 24 hours in 1 day. And this is supposed to be in hours, right? So, and then of course there are 365. Let's just say 0.25. It's fine. Days in 1 year. All right. So anyhow, you take this number, 1 times 10 to the 21st seconds, divide by 60, divide by 60 again, divide by 24, and then divide by 365.25, and you get the answer to this problem number 6, which is 3.2 times 10 to the 13th years. All right, so 3.2 times 10 to the 13th years. Just for our own benefits, just to make a little more sense of this, I'm going to move the decimal place 1 place to the right. And if I do that, of course, I have to reduce the scientific notation by 1. So this becomes 32, and you'll see why I'm doing this in just a second. 32 times 10 to the 12th years. All right, so another way of saying that would be 32 trillion years, all right? So, this time is enormous. The universe is not that old. It's not even close to being that old, right? The universe, as we'll find out later in the semester, is about 13.8 billion, right? So like the age of the universe is 13.8 billion, means times 10 to the 9th years, right? So this time right here, which we calculated, if this was the constant rate that the sun was losing energy, it would last many times the current age of the universe. As we're going to see a little bit later, that is certainly not the situation. All right, let's look at the next problem. And give me a second here. Let's see, where is it? All right, so the next problem, let's go back to this. All right, and so the next problem, let's get out of that, says, use the information presented in the chapter to estimate the radius at which the speed of protons in the corona first exceed the solar escape speed. All right, so we got to know what the solar escape speed is. All right, let me set this problem up. Let's go back to this. And what we're doing is, let's see, we need a new. All right, very nice. And all right, so let's see. So this is number 7, isn't it? Let's see. Yeah, here we go. So the first thing is you got to look up the escape speed from the sun. I don't know that you guys need to calculate that. So here, this is number 7. I think what they want you to do, let me just show you how to do it. It's actually fairly easy. We'll just look at, we'll just look up. All right, so the escape speed from the sun is 618 kilometers per second. All right. They have, like, to calculate that, you need to use an equation that we didn't encounter because it's from chapter 2. But anyhow, it's the square root of 2 times big G, which is the universal gravitational constant, times the mass of the sun divided by the radius of the sun. All right, so that's, you look up all these quantities, G, M, the mass of the sun, the radius of the sun. Anyhow, you get this value. It would come out in meters per second. It's like 618,000 meters per second, so it's just easier to put it in kilometers per second. All right, so anyhow, I think the thing that they want you to do is to use the following, right? The temperature in the corona, right? So the temperature in the corona. Basically, what we're going to do is we're going to find that the escape velocity. So v escape. This is actually in chapter 16, so that's why I think this is the way they want you to do it, is equal to a constant. Let's see. So what is it? It's a constant divided by. Let's see. It's going to be. It's this constant, which is 0.157, sorry about that, 0.157 times the square root of the temperature of the gas, and then it's divided by 1. The reason it's divided by 1 in this particular case, that would be like the mass of, the atomic mass of the gas. And since hydrogen just has 1 proton, the atomic mass would be 1. So if we set this equal to this value, then what we can do is we can figure out what that escape speed would be. All right. So anyhow, let's do this. All right, so let's see. So what did we do? So that is. Let's see. So what we're going to do is we're going to use the temperature of the sun, or the temperature of the corona as 3 times 10 to the 6, 3 million Kelvin. All right. So this speed, actually this is the sorry, this isn't the escape speed right here. This is just the speed of a gas, right? So this is just don't think about the, here, let me erase that. Don't think about the escape speed right here. The escape speed is just that's actually the escape speed from the surface of the sun. All right, so that's something that you just look that up. I mean, it's really comes from this equation that you do in chapter 2, but we're not really covering that. Anyhow, so this is just the velocity of a gas at some temperature. All right, so it's equal to 0.157 times the square root of the temperature divided by the mass of the gas, which in this particular case, since it's hydrogen, it's just 1. All right, so anyhow, it goes like this. It's going to be, so the square root of, they give us the temperature of the corona, so we're going to use 3 times 10 to the 6th times 10 to the 6th, and of course that has to be in Kelvin, and of course it's going to be